is band theory of solids. Now previously we have discussed here the free electron theory, which was successful in explaining various electronic as well as thermal properties of metals, such as this specific heat as well as the paramagnetism. But it was not able to explain why certain metals have a large number of free electrons whilst others don't have. So basically it was not able to explain the differences between a conductor, a semiconductor and an insulator. Also, it was not able to explain the variation of resistivity with temperature for insulators. Now, the cause of failure for this free electron theory was its oversimplified assumption that a conduction electron in a metal, it experiences a zero or a constant potential due to the iron core. Hence, it is free to move about in a crystal. But in reality, we will see that in the actual nature of this potential under which this electron moves in a crystal is very complicated. And because of that, it was not able to explain the differences between conductor, insulator and semiconductors. Also, from the free electron theory, we have seen the variation of energy as a function of wave vector k, that is the dispersion relation, as equal to hk square k square divided by 2n. So here if you see that there is no upper limit to the energy, and this k value can have discrete values, which means that these energy levels are discrete and may have any spacing depending upon the dimension of the box. So basically the energy, it is representing the energy of a particle in a box. So if you remember, the energy of a particle in a box is given by hk square pi square n square divided by 2m a square. This a is the dimension of the box. So depending upon this a value, this energy can take any value, so that the energy spectrum forms a discrete energy levels. Now we will see the modified version of this free electron theory, that is the band theory of solids. Now this band theory of solid, it is based on the assumption of periodic potentials with period equal to the lattice constant. So the band theory of solids was based on the assumption of periodic potentials with period equal to the lattice constant, and this assumption is based on the fact that these iron cores in the crystal, they are distributed periodically on the lattice sides. So basically we are considering a crystal. So the crystals have a periodic distribution of atoms, right? So these iron cores, they in the crystal, they are distributed periodically, and the potential contribution due to all other free electrons may be taken as a constant. Now this type of periodic potential, it extends up to the infinity in all directions except at the surfaces where the periodicity of this crystal, it breaks. Now this particular graph, it is representing this periodic potential which is extending up to infinity, and at the surface there is a break in the periodicity, so the potential, it is a little bit higher, so that the electron, it is very difficult for electron, it is very difficult to move out of the surface. So it will require a work function for this. And you can also see here that this red dots, it is representing the atoms, or basically the ions, positive ions, and they are distributed periodically with a lattice spacing of a. So any electron, if it is traveling with energy E greater than this particular V naught, if I say this is V naught, so it can easily travel through this lattice. But if it has a lower energy, then it may trap in the vicinity of any one of these ions. Now this periodic potential, it forms the basis of the band theory of solids, and the behavior of electron in this potential is described by constructing an electron wave function using one electron approximation. In one electron approximation, we assume that the field experienced by a particular electron is a resultant of the field due to the fixed nuclei and the average field due to the charge distribution of other electrons. So there could be other electrons also. So the net field experienced by a particular electron E is because of this potential, because of this nucleus, fixed nucleus, and the charge distribution of other electrons. Now let's see the outcomes of this periodic potential. So first of all, there exists a loud energy band separated by a forbidden gap. So we will see that in this periodic potential there are energy bands. So whereas in the free electron theory, we got a discrete energy levels where in between two energy levels there was nothing, right? But in this case there are a lot of energy levels packed inside this particular range DE, and this forms a band. And the outcome of this periodic potential is that there exists some allowed bands as well as some forbidden bands. We will also see that the electronic energy functions is a periodic function in the wave vector. Now, this existence of this band gap is the most important new property which emerges when the free electron model is extended to include this periodic potential case. Now, let's talk about important theorem, that is Bloch theorem. As we know that for free electron theory, the 1D Schrödinger wave equation for an electron moving in a constant potential V naught, we have solved the Schrödinger wave equation as h square divided by 2m, then the double derivative of wave function plus V naught and then psi equal to E psi. And we have seen that the solution of psi in this case are represented by a plane wave which is given by e raised to power plus minus iota kx, where this E minus V naught, it is representing the kinetic energy which is equal to p square divided by 2m or h square k square divided by 2m. But here in the band theory we have a different situation. Here we have one-dimensional periodic potential V of x. So therefore, for V of x, the Schrödinger wave equation becomes d square psi by dx square plus 2m divided by h square e minus V of x then psi of x equal to 0. Now since this potential it is periodic with period equal to the lattice spacing, that is a, so we have V of x equal to V of x plus a. Now this Bloch theorem is concerned with this solution for this particular Schrödinger wave equation. Now according to this theorem, the solution of this equation are the plane waves of this particular type e raised to power iota kx, which are modulated by a function uk of x, and this uk of x has the same periodicity as v of x. So therefore, according to Bloch theorem, the solution for this Schrödinger wave equation for a periodic potential are given by psi of x equal to e raised to power plus minus iota kx, that is the plane wave solution, and it is modulated by a Bloch function, that is uk of x. With uk of x is also periodic, so that uk x plus a is equal to uk of x. So this particular type of wave functions, they are known as Bloch's function. Here we will avoid the proof of this Bloch theorem and we will directly go to Kronig-Penney model. Okay, now let's come to Kronig-Penney model. So this model is a relatively simpler model which explains the behavior of electron in a periodic potential. This particular model, it assumes a relatively simple one-dimensional model of periodic potential as shown in this figure. So if you have seen the previous potential, in comparison to that, we have made a simpler approximation of the periodic potential by considering a periodic square wells. So the potential energy of an electron in a linear array of positive nuclei, it can be assumed as a form of periodic array of this square wells with period equal to a plus b, where at the bottom of this well, that is from 0 to a, the potential energy is taken as to be 0, while outside the box, that is for this 0 to minus b, or in the second region, the potential energy is a constant v naught. Although this model employs a very crude approximation, yet it is very useful to illustrate various important features of the periodic lattice, such as the band formations. Now we will be solving Schrödinger wave equation in these two particular regions. In region 1, the Schrödinger wave equation for x less than a and greater than 0, the Schrödinger wave equation will be given by double derivative of wave function plus 2me by h cut square and then psi equal to 0, since there is no potential v. And in the second region, where this x is in between 0 and minus b, the Schrödinger wave equation will become d square psi by dx square plus 2m divided by h square times e minus v naught, y equal to 0. Here we are assuming bound state of electron. So this means that E is less than V naught. And we will define two real quantities, alpha and beta, where alpha square is this particular value, 2me divided by z square, and beta square is a negative of this particular value. So therefore, the equation 1 and equation 2 will become d square psi by dx square plus alpha square psi equal to 0 and b square psi by dx square minus beta square psi equal to 0 for region 1, and this is for region 2. Now, since the potential is periodic, the wave function must be of the form of Bloch functions. So therefore, psi of x must be equal to the plane wave type solution and modulated by uk of x, where this uk of x has the periodicity of a plus b. Therefore, uk of x must be equal to uk of x plus a plus b. So this result is from Bloch's theorem. Now we will differentiate equation 5 twice, so that we can put in equation 3 and 4, and we can find the solution for these Schrödinger wave equations. So let's try to differentiate equation 5. So what we will get is d psi by dx is equal to differentiate first and keeping the other constant, it will give iota k e raised to power iota kx uk of x plus e raised to power iota kx, and differentiation of second will give you duk of x by dx. And we can take the second derivative also, so that will be equal to d square xi by dx square. So that will be differentiation of first, and keeping the other constant will give you iota k whole square, then e raised to power iota kx uk of x, plus keeping this constant iota k e raised to power iota kx, and then differentiation of second will give you duk of x and dx, and then plus differentiation of first will give you iota k e raised to power iota kx, and then duk by dx, and then finally the derivative of this will give you e raised to power iota kx, and then d square uk by dx square. You can simplify this, so you will get minus k square e raised to power iota kx uk of x, and this is the same thing, so it will be twice iota k e raised to power iota kx duk by dx, and then this last final term, so that will be e raised to power iota kx, and then double derivative of uk of x. Now what we will do is we will substitute this d square psi value here in equation 3 and 4 for these two regions. So equation number 7 in equation number 3, so you will get, where I have used the equation 5 also. So here you can see, you can cancel out this common term e raised to power iota kx, so that the simplified equation will become d square uk by dx square, and then plus 2 iota k duk by dx, and then alpha square minus k square uk of x equal to 0. Now if you see here, this is a second order differential equation, and we can find its solution by d operator method. So here if you see that the roots of this particular equation will be iota alpha minus k and minus iota alpha plus k. So these are the two roots of, if you solve the by d operator method, then you will get these two roots. So therefore the value of uk in the first region is given by u1 is equal to a e raised to power iota alpha minus k plus d e raised to power minus iota alpha plus k x, here also x. So this is for the first region, that is in between 0 and a. And similarly you can put equation 7 in fourth equation, that is in the second region. So here if you put equation number 7, then you will get, and here also you can cancel out this common term e raised to power iota kx. So here also you will get the similar sort of equation. So again, if you see here, this is a second order differential equation. So this has a roots equal to beta minus iota k and minus beta plus iota k. Therefore, the value of uk in the second region will be equal to c e raised to power beta minus iota k x plus b e raised to power minus beta plus iota k x for minus b to 0. So these constant a, b and c and d, they can be found by applying the boundary condition and the condition of periodic potential. So the boundary conditions are given by that this u1 in the first region at x equal to 0, it must be equal to u2 at x equal to 0. and the derivative must also be a continuous. So this means that du1 by dx at x equal to 0, it should be equal to derivative of u2 at x equal to 0. And similarly, at the periodic potential condition will give you u1 at a, it must be equal to u2 at minus of b, and the derivative also will be continuous. So du1 by dx at x equal to a, it must be equal to derivative of second at x equal to minus b. So this means that here the value of wave function at x equal to a and x equal to minus b, so this represents a similar sort of environment, so there should be a continuity in between the wave function. So if we apply this boundary condition to above this un and u2 function, then we will get from this particular condition, we will get a plus b, it must be equal to c plus d. And the derivative condition will give you iota alpha minus k, this term will become in front, so it will become a iota alpha minus k minus b iota alpha plus k, it must be equal to c beta minus iota k minus d beta plus iota k. So this is also done, and this third condition if you put, then you will get a e raised to power iota alpha minus k, and then a, it must be and then plus b e raised to power minus iota alpha plus k, a, it must be equal to c e raised to power minus beta minus iota k, then b, and plus b e raised to power beta plus iota k, b. So this is also done, and the final condition will give you a iota alpha minus k, and then e raised to power iota alpha minus k a, then minus b iota alpha plus k, and then e raised to power minus iota alpha plus k a, it should be equal to then the second derivative, so that will be equal to c beta minus iota k, and then e raised to power minus beta minus iota k, and then b, and then minus d iota b plus iota k, and then e raised to power beta plus iota k, and then b. So this four equation first. So you will get a system of linear equation with the constant values, so that after solving for boundary condition, you will get a system of linear equations in this variable a, b, and c, d. So these equations, they can have a unique solution if and only if the determinant of the coefficient of this a, b, and c, and d, the so this system of linear equation will have a unique solution if the determinant of the coefficient of this a, b, c, and d, it vanishes. So this implies that we have to make the determinant of the coefficient of a, b, and c, and d. So this is the determinant of the coefficient of a, b, c, and d, and its determinant should be 0. So this is very tedious to solve this particular determinant. So I'm just putting the direct result of this determinant. So on solving this determinant, you will get alpha square plus beta square divided by 2 alpha beta, and then sine hyperbolic beta b, and then sine alpha a plus cos hyperbolic beta b cos alpha a, it should be equal to cos k a plus b. So this is the condition which is required for the existence of wave functions in this periodic potential. So now, in order to simplify this equation, Kronig and Penney, they considered it the case when this V naught is very large, so it is tending to infinity, and the the size of the width of that square well, it is very small. So this B is tending to 0, but this V naught times B, its value is finite. So if you have seen our previous video on Dirac delta function, so this particular thing is representing a Dirac delta potential. So under these circumstances, the KP model is modified to one of the series of wells which are separated by infinitely thin potential barriers, and the quantity that is limit V naught tending to infinity and B tending to 0, and then this V naught times B. So this quantity is known as barrier strength. Now let's see how this particular condition for the existence of wave functions it gets modified under this limits. So for B tending to 0, the sine hyperbolic beta b, this particular function, it can be approximated as beta b, while the cos hyperbolic beta b, it can be approximated equal to 1. Also, you remember we have defined our alpha square as 2me divided by hk square and beta square as 2m v naught minus e divided by hk square. So therefore, alpha square plus beta square will give you 2m v naught divided by hk square, and alpha square plus beta square divided by 2 alpha beta will give you, this 2 can cancel this 2, so you will get m v naught divided by alpha beta times hk square. We'll substitute all these values in the equation which represents the condition for existence of a function. So therefore, this equation will become m v naught divided by alpha beta hk square, then sine hyperbolic beta, this will become beta b, and sine alpha a plus cos hyperbolic beta 1, this will be 1, and so here it will be cos alpha a, and this must be equal to cos k a plus b. Now here you can see this beta will get cancelled, and whatever remaining thing is, we can define it as p value. So this quantity p is a measure of the area, this is v naught times b of the potential barrier, and the increasing p has the physical meaning of binding the electron more strongly to a particular well, and we will see how this influences the motion of electron in the lattice. So therefore, our condition will get modified as p sine alpha a divided by alpha a plus cos alpha a equal to cos ka, where this p was equal to m a v naught b divided by hk square. So here you can see that it is proportional to the area of the potential barrier. So larger the potential barrier, the area of the potential barrier, the larger will be P, and which signifies the binding energy of electron. So this is the important result from the Kronig-Penney model, and we will show how this particular equation gives rise to the formation of band. Now, in order to see the formation of bands, we will plot the left hand side of this particular equation separately and the right hand side of the equation separately. So let me define function of alpha a as p sine alpha a divided by alpha a plus cos alpha a. So this is the left hand side of this particular equation, and that should be equal to cos k a. So now if you remember, this cos k, or basically any cos function, has a maximum value of plus minus 1. So that this left hand side function, its value is limited to plus minus 1 via this right hand side of this particular equation. So let's plot the left hand side of this equation. So this is this particular graph, it is representing the f of alpha a. So that is the left hand side of that particular equation, and we have seen that the right hand side, that is the cos ka value, it is limited, its value is limited to plus minus 1. So there is a condition that the left hand side value, it should not exceed plus and minus mark. Therefore there is certain allowed values of alpha a possible, while other values of alpha a are not possible. So let's identify the values of alpha a for which this graph of function of this alpha a, it is in between the limits of plus minus 1. So here you can see that here in this particular region, this green region, the value of this blue curve, its value is lying inside plus minus 1 mark, and while exceeding this green boundary in the black region, its value is going above plus 1. So that particular region is not allowed. So, and similarly you can see there exist only certain values of alpha a for which the solution of wave function inside the periodic potential can exist. Now if you remember, our alpha square was directly proportional to E, so this means that alpha value is directly proportional to e raised to power half. So as we have seen in the graph that only certain values of alpha are allowed. So this means that only certain values of E will be allowed. So therefore, in the band theory of solids, there exist certain allowed bands of energy and some certain forbidden bands of energy. While if you remember, in case of free electron theory, there was no concept of band formations. So it was only because of the periodic potential and this Kronig-Penney model that we were able to explain the formation of bands for the first time. As I told earlier that since alpha square value is proportional to energy E, this epsiska is a measure of energy. So I have taken the allowed values of alpha A and I have make them horizontal to represent the energy bands. So here on the right hand side you can see the formation of energy bands. So here you can conclude that from Kronig-Penney model we can see there is a formation of energy bands, and this energy spectrum of electron, it consists of alternative regions of allowed energy bands, that is this solid green regions, and they are separated by a forbidden energy band, that is this black region. If you notice here that the width of each allowed energy band, it is increasing as this alpha A, it is increasing. Here also you can see the energy allowed bands, the width of energy allowed bands, it is increasing with increasing energy. Now let's see the effect of barrier strength on the formation of bands. So here, for example, I have taken the barrier strength as 5. So if I am increasing the barrier strength to 24, then you can see that the width of the energy allowed bands, it is reducing. And if I made the barrier strength infinitely high, so for this P tending to infinity, the energy allowed bands, they are compressed into energy levels. So the bands will become energy levels and a line spectra will be resulted. While if I make the barrier strength 0, then you can see there is a complete band, and these energy values, there is no forbidden gap in between the energy bands, or you can see that every energy level is possible. So if you remember, we have seen in the case of free electron theory that the electron can possess any energy level since it is not interacting with anything. But in case of barrier strength, or basically when it is interacting with the lattice, then or the periodic potential, there is a formation of bands, as you can see here. So from Kronig-Penney model, you can see the two limiting cases of barrier strength P. When the barrier strength P is 0, then you can take that case as completely free electron case where all energies are allowed and there is no formation of bands, while the other case is for when this barrier strength P is very large. So in that case, it is very difficult for an electron to escape from the potential well. So it is kind of trapped in a potential well. So in that case, the energy levels follow the particle in a box energy levels, as the tunneling through the barrier becomes very difficult. So this particular case, when P is very large or the barrier strength is very large, it is representing the case of insulators. Because in insulators, for an electron it is very difficult to come out of the vicinity of nucleus. While in case of free electron, it is not the electron is not affected by the influence of nucleus, so all energy levels are possible. Let's see the limiting cases of when P is tending to infinity from this particular equation. So in case of P tending to infinity, you can divide this particular equation by P. So you will get sine alpha A divided by alpha A plus cos alpha A divided by P equal to cos Ka divided by P. So in case when this P is tending to infinity, so the second term and third term will be 0. So this implies that sine alpha A divided by alpha A, it must be 0. So now if you remember, so this is possible only when alpha A is equal to n pi, where n cannot be equal to 0, otherwise this will be 0 by 0 form, right? Now if you remember, we have defined it alpha square as 2m E divided by h cut square. So therefore E will be equal to h cut square alpha square divided by 2m. Or you can substitute the value of alpha from here. So energy will be equal to h cut square, then alpha square will give you n square pi square divided by 2m a square. So if you remember, this is the energy levels for the case of particle in a box. So what is the physical meaning when P is tending to infinity is that the barrier strength here is very large. So in that case, the electron will be trapped inside any one of the square well. Now let's see the other limiting case, that is when P is tending to 0. So when P tending to 0, then cos alpha A, it must be equal to cos Ka, or alpha must be equal to So if you remember this alpha value, it is related with E as this relation, so we can relate E is equal to alpha square h cat square alpha square, so that will be k square divided by 2m, and here you can see that E is proportional to k square. And if you remember, this is the dispersion relation for a completely free electron. So this is it for today, and in the next video we will see the formation of band in great detail, and we will also see the differences between insulator, conductor and semiconductor, and the concept of effective mass.